Sir.
Okay, so I am going through the book that I shared with you. This is Transients in Power System, and we'll start from chapter 1 today. So if we look at the content of this book, so today we'll basically cover the basic concepts and simple switching transients. So what happens if we switch a RL circuit or LC circuit and RLC circuit in AC network. And afterwards, in the upcoming classes, we will see the transient analysis in three-phase power system. Many of these things may become familiar to you, like the symmetrical components and the sequence components of unbalanced network, the sequence networks, the analysis of unsymmetrical three-phase faults like this. And then before mid, we will also have traveling waves. So this is very important topic that we will cover, inshallah, before mid. And lastly, circuit breakers. So up to mid, I hope to finish until circuit breaker, chapter number 4. Okay, so let's start with chapter 1, the basic concepts and simple switching transients. So if you have any question, you can, feel free to ask me at any time during the lecture. Okay. So basically we'll try to see today about the RL circuit switching, LC circuit switching, and RLC circuit switching. The reason we are doing this is because the power networks that we have in a power system, we have normally generators, and then this generator is connected to transformer, which steps up the voltage, and then you normally have a transmission network. So the power is transferred through the transmission network. And then again, you have transformers to step down the voltage, and then which is basically connected to home or industries, depending on the voltage level, right? Do you understand what I'm trying to say?
Yes, sir. Yes, sir.
Yes. So
Yes, sir.
the household voltage level, for instance, this is 230 volt. At the industry, it can be connected to 11 kilovolt or 33 kilovolt if the industry needs heavy powers like this. And so basically, you have the power infrastructure is like this. And we can model these different components like the transformers. The transformers can be modeled like a inductor and a resistance. And then can you recall these things from your machine course maybe? The transformer is modeled somewhat like this, right?
Yes, sir.
Yes. And also in the secondary, you have resistance and inductance. And in a very simplified model, as the current which is coming through the primary, as most of the current is basically going through the secondary, and a very small amount of current is actually flowing across these shunt components. So you can basically ignore it for a time being, and you can model the transformer in a very simplified way, like a inductor and a resistance, like this. The same is true for transmission line. The transmission line, you can model this transmission line by a resistance and a inductor. Why? Because this transmission line has a certain amount of power that is dissipated in the line, which is termed as I square R power loss. So because of this I square R power loss, you have, I mean, if you send a certain power in the receiving side, you do not get the exact power that you send. Some part is lost. That means, of course, there is a resistive component here. So there is a certain resistance that we normally can model as a lumped component. As a lumped component means that you model all the, let's say this is our sending end A and this is our receiving end B. So all the resistances you basically model as a single resistance. Okay. And of course, you have also inductances here, as this is AC network. So you have L and you have R, right? And again, this transformer, which is basically R and L, like this. And you have some stray capacitances in the line. You have certain capacitances in the line. Why you have capacitances in the line? Because this transmission line that you have is basically, this is at high voltage. This is at high voltage. And you have a ground here, so which is elevated. This transmission line is placed at a certain height, let's say 10 meters or 15 meters away from the ground. So basically you have a one conductor, and then you have a certain distance here, and you have another part which is grounded. So basically you have two, two conductors placed at a certain distance. Within this is basically air. So air is a dielectrics, and then you apply some voltage, which makes it a capacitor. So you have certain capacitance here, which is not, of course, you cannot see it in your open eyes, but this capacitance exists, right?
Yes, sir.
Okay, so what we have is basically now we can represent this power network by simple R, L, and C, RLC circuits. Okay, and of course, this lumped representation, that means if we represent this whole network like in a pi model. Have you heard of this transmission line model, equivalent pi model or equivalent T model?
Yes, sir. On 4-1.
Yes. So that means that we can represent this transmission line. If you have a large transmission line, we can represent it as a, for a pi model, we have pi by, it's C by 2 here. And then we have R, L, and then again C by 2 here. So the whole network, this is from point A to point B. That means whatever you have in the transmission line, you can basically represent it using lumped components like resistance R, inductance L, and then capacitor divided into two parts placed at two places. And A is the sending end and B is the receiving end. So this is called the lumped representation. If the line is short, you can simply present it like an R and L. So this is your R, this is your L, and you can get rid of this C. If the line is short, you can assume that the capacitance is not very big, because this capacitor R will increase if the line is long, as every line has its own capacitance, and this capacitance adds up as these are placed in parallel. So if the line is not very long, for instance, if it is less than 80 kilometers, then we normally ignore this C and then represent this using R and L. And the whole reason we do this, convert it to R and L, is that we can do the calculations. So we can apply Kirchhoff's law, we can apply Kirchhoff's voltage law, Kirchhoff's current law, and solve the circuit basically to get, for instance, if we have a certain sending end voltage, if we know this value of RL and C, then we can calculate what's the value in the receiving end. If we send a certain current flowing through this line, for instance, in this line, if you have 1000 ampere current flowing, then we can calculate how much power is being lost into the line and how much voltage will we get at the receiving end. So these kind of calculations we can do easily. So these are the this is what we normally do in static calculations. So in a steady state calculations, by steady state, I mean that when you do not have any sudden change in the system. For instance, if the system is running at what it should run at normal condition, for instance, at 50 hertz and at a certain voltage level, if the transmission level is 132, so the voltage is around 132 kilovolt. So at that time, you can represent this circuit using RLC components and use Kirchhoff's law to solve the problem. Am I clear up to now?
Yes.
কারো কোনো সমস্যা আছে বুঝতে এখন পর্যন্ত?
No, sir.
Okay. But if there are certain times, for instance, when you have very fast changing voltage or currents, it can come from outside environment like a lightning. So it may happen that you have a lightning hit on the line, on the transmission line. Lightning is basically a high value of current. So you have I of t, which basically hits the transmission line if it hits. So this I of t can be, the value of I is the shape of the lightning current. So if you measure the lightning current in y-axis, you have I of t. So this is current. And in x-axis, this is t. Then this duration of the lightning is normally very short. It's around 50 microsecond. Now note this power system frequency is 50 hertz, which is basically gives you a time period of 20 milliseconds. So each time period will be 20 milliseconds for a 50 hertz signal. And lightning current is very short. It's only 50 microsecond, not milli. So this very fast transient current, when it hits this line, then it sees two paths. One is on the right and one is on the left. And depending on the resistance, it will split into two parts. So one will go into the light, one will go into the right, and another will go into the left. Now, because of this resistance and lightning, it will develop a voltage V, which is basically this I and R. So I multiplied by this R, it will develop a voltage, which is of course of very high frequency because you have very short time duration for the whole current and as well as for the whole voltage. So that means that you will have, for a very short amount of time, you will probably see a sudden high peak of a voltage, which will appear on top of the supply voltage, on top of the system voltage. You will see a very short duration, high amplitude voltage transient. So this voltage transient, as this is of very high frequency, so you cannot use this Kirchhoff's voltage law. You cannot use the Kirchhoff voltage law because as the frequency is high, so I mean the physical distance from point A to point B, if this is several hundred kilometers, then the wavelength is not, I mean, is shorter than, if the wavelength is shorter than this whole distance, then you cannot use the Kirchhoff's voltage law. In case of 50 hertz system, the wavelength is very long, so you can use basically you can use the Kirchhoff's voltage law for a 50 hertz system for 50 when analyzing 50 hertz. But when you analyze the transient, which is basically of very fast or short duration, for instance, in this case, we are discussing about the lightning induced transients. You can also have switching transients. That means when you open the circuit breakers, then we will also have a transient like this. So analyzing these transients, you cannot represent the circuit just by a lumped R and L. Instead, you have to use a different modeling techniques to represent the circuits instead of just lumped components. So instead of lumped components, you may have distributed components, like you have several R and C placed at alongside the line, and you have to consider what's the duration of this transient, what's the frequency, and depending on that, you have to model the components. Am I clear? Do you have any question up to now?
No, sir.
Okay, so that's what here actually in the book is in the beginning is tried to say, that the purpose of the power system is to transport, distribute electrical energy generated in the power plants consumers in a safe, reliable way. Aluminum and copper conductors are used to carry currents, transformers energy to the appropriate voltage level, and generators are used to take care of the conversion mechanical energy to electrical energy. Okay, so when you speak of electricity, we think of current flowing through the conductors from generator to the load. This approach is valid because the physical dimension of the power system are large compared to the wavelength of the current and voltage. So for 50 hertz signal, the wavelength is 6,000 kilometer. So this wavelength is for 50 hertz. This is very large, but for a higher frequency, if the frequency is very high in the range of several hundred kilohertz or megahertz, in this range, this wavelength becomes shorter. Okay, because we know, I mean, what's the relation between wavelength and frequency?
So inverse, sir.
So V is equals to F lambda. Yes. So it's inverse. So if the frequency is high, the wavelength goes down. So this enables us to apply Kirchhoff's voltage and current law using lumped elements as shown here. So you can use lumped elements when you use 50 hertz signals in our modeling of the power system. In fact, the transportation of the electrical energy is done by electromagnetic fields surrounded. Okay. So for steady state analysis in the power flow, when the power frequency is constant, we can successfully make use of the complex calculus and phasors to represent voltage and current. So that's what we do when we solve the steady state problems, or let's say when we do the load flow analysis, then we use this steady state analysis and represent the power network like lumped components. Power system transients, however, involve much higher frequencies up to kilohertz and megahertz. So this is very important. So frequencies change rapidly and the complex calculus cannot be applied any longer. Now the differential equations describe the system phenomena have to be solved. So instead of using complex calculus and phasors, now we have to use differential equations to describe the phenomena. Okay, so differential equations means that this is the this is the main equation describing the circuit. We'll see it. You are of course familiar with this technique. Okay, so in case of power transformer and non-frequency condition, the transformer ratio. Okay, so here is again another important thing is mentioned. So let's say in a power transformer, so we know that the power transformer is so let's say this is our core of the transformer, and then on top of the core you have the windings connected to here. So let's say this is our primary winding and this is our secondary winding. Okay, so depending on the turns ratio, let's say in primary winding we have NP turns, and in secondary winding we have NS turns. So in the if let's say NP is small than NS, so it will act like a step up. So if we have a certain voltage VP and certain voltage VS, so VS will be basically increased by the ratio NS divided by NP in normal condition in the 50 hertz in the 50 hertz system. But if you have a transient, then what happens is that basically because these windings are placed on like this, so you have small capacitors basically in between the windings. Do you know that? Do you know that there is also a capacitor that exists between the windings?
No, sir.
Okay, so let's say the transformer winding. Okay, so the actual winding of a transformer looks like this, right? Can you see my?
Yes, sir.
Yes. So let's say this is the top part of the winding and this is the bottom part of the winding, right? So this makes like in let's say if you look at here, so this is the top part, let's say T, and this is the bottom part, let's say B. So this is one winding. This is the top part and this is the bottom part, and you see that the windings have a certain gap from one another. In between this winding, you have normally certain insulation to protect this winding from short circuit. So if you do not have any insulation, then this top part and the bottom part will be shorted and the current will flow just through the shorted path, right?
Yes, sir.
So you do not want your current to flow between the shorted path. Instead, you want your current to flow through these windings. And that is why you have to have certain insulation between the windings. That is what you can see it from this paper insulation. So on top of these windings, you have basically paper wrapped on this windings. Now what happens is that from this top to bottom, you basically give your voltage VP. Now in a steady state condition, if let's say if you have 10 windings from top to bottom, let's say you have only 10 windings, and if you have VP here, then across each of these windings, you will have VP divided by 10 voltage, isn't it?
Yes, sir.
So this VP by 10 voltage, as you have 10 windings, so each one will have VP by 10 voltage, and you basically add all this, and all together from the top to the bottom, you will have VP voltage in the normal operating condition. So basically in the normal condition, the voltage that is distributed from each of these windings is VP divided by 10. And as there is a voltage difference between the first winding and the second winding, so you have a voltage of VP by 10 and you have a certain insulation. So basically you have two conductors and you have an insulator in between. So basically, and the voltage here is VP by 10. So basically you can represent this as a capacitor, right? The capacitor is the same. The capacitor, you have two electrodes, and in between these two electrodes, you have a certain insulator, and then you apply a voltage V and the ground. So this will makes a capacitor, isn't it?
Yes, sir.
So basically, the transformers will also have capacitors between these windings, between each of these windings. Small capacitors that is not visible in your normal eyes, but of course, if you are an engineer, you have to see these capacitors. You cannot see it normally. Then general people will not see these capacitors, but you understand that there is a capacitor between each of these windings. Okay, now there is small capacitors, let's say C, small value of this capacitor C. Now, when you give a sudden transient voltage, which changes very fast, so this transient voltage, when it comes, then instead, as the frequency is very high for the transients, in power frequency, this is 50 hertz, but for the transients, it's several kilohertz to up to megahertz. So the frequency is very high. Now we know that the capacitors XC is basically 1 over j omega c. So this C is fixed, C is there, but as omega is very high, as this omega, which is basically twice pi f, as omega is very high, so that means XC will be very low. So this capacitance impedance coming from this capacitor will be very low, and the current will flow capacitively instead of flowing through these windings. So these capacitors will define the voltage distribution. So how much voltage will be distributed between each of these windings will be defined by the capacitor instead of the inductors in the winding in the transient phase. Am I clear? আমার কথা কি বোঝা গেছে?
Yes, sir.
Okay. So that's what here they try to say. So in case of a power transformer under normal frequency operation condition, the transformer ratio is given by the ratio between the number of the windings of the primary coil to the number of the windings in the secondary coil. However, for a lightning induced voltage waves, the stray capacitance. So the stray capacitance is basically this capacitance. This is not seen by open eye, but this exists, and as a result is called stray. It comes naturally. I mean, if you have a transformer, this capacitor will always arrive. So you cannot get rid of these capacitors. So this stray capacitance of the winding and the stray capacitance between the primary and the secondary coil determine the transformer ratio. That means that this stray capacitance will define how much voltage will be transferred to this side, or how much the voltage will appear across these insulations. Okay. In this two situation, the power transformer has to be modeled differently. And of course, yes, in the previous case, we normally, when we model it for steady state analysis, we do not consider these capacitors. But when you have transient analysis, you have to always consider these capacitors that is not seen in open eye. Okay, আমি কি বুঝাইতে পারতেছি?
Yes, sir.
কারো কোয়েশ্চেন আছে এখন পর্যন্ত? Any question up to now?
No question, sir.
Okay, so I continue then. So basically in this part, it says that how the transient phase is different from the normal 50 hertz components. Okay, and then basically in the book, it gives some of the examples, like when you switch an LR circuit or when you switch an LC circuit, what happens to the transient phase, and what is the steady state phase and what is the transient phase. Okay, so first we come to the switching of an RL circuit. So a RL circuit is shown like this. So you have a inductor L and resistance R. So again, this is very important, very useful, because you represent the power network using these resistances and inductances. In the steady state case, as well as in transient case, you also represent it by using R and L, but differently. So if you understand the basics of what happens if you switch this R and L circuits, then you will understand the basic parts. Am I audible? Ami ki connected achi?
Yes, sir.
Okay. Okay, so a sinusoidal voltage is switched on to the series connection of inductance and resistances. So you have a sinusoidal source here with a series connected LR circuit, and then you have a switch. This is in the fact most simple single phase representation of high voltage circuit breaker closing into a short circuited transmission line or short circuited ungrounded cable. The voltage source E represents the electromotive force of a synchronous generator. L corresponds to the the inductance corresponds to the synchronous inductance of the line. So as I mentioned previously already, this reactance from the generators, reactance from the transformer, reactance from the line, this basically represents this L, comprises of this inductance of this generator, leakage inductance from the transformer, inductance from the bus bar, cables, and transmission line. Resistive part is basically the losses that is in the line R, and E is the voltage source. So voltage source E is basically from the generators. So you can, ideally, you can represent the power network in a very, very simplified way like this RL circuit. And if you have a circuit breaker, if you close this circuit, then we'll try to understand what happens to this circuit. This is familiar to you. I believe you have already solved this kind of problems in your undergrad studies. Okay, so because you have linear networks only, the current flowing in the circuit after closing can be seen as a superposition of a transient current and a steady state current. Okay, so you have, if you apply the Kirchhoff's law, then you have E max sine omega t. So this is the source, is equals to Ri, the voltage drop across the resistance, plus L di dt. So this is the voltage drop across the inductor. And if you close it, so the Kirchhoff's voltage law gives us the equation, this one. Okay, so this equation has, I mean, it has two parts. If you, I mean, this is differential equation. If you look at here, one, it says that this voltage source E max sine of omega t, it will be Ri plus L and derivative of di by dt. That means derivative of the current. So as you have a derivative here, so this is a differential equation, and the solution of this I should be such that you see that the right hand side is Ri plus L di by dt. So you have a current, should be a function, it should be a certain function that you do the derivative of this function, you again get the same function so that it becomes a sinusoidal. So that's what this equation tells us, is basically, so you have a I component here plus a derivative of I that will give you a sinusoidal. Now, what kind of functions has this characteristics that that the derivative of this function will also be the same as the original function? This is basically an exponential function. So if you have a, if the solution is an exponential, so let's say if I is an exponential function, so the derivative of this I will be also an exponential, and we know that this sign can be represented by exponentials. So one is a it can be an exponential, and the other is it can be sinusoidal or cosine function. So if I is sinusoidal, the derivative of I is cosine. So cosine is again a sinusoidal with a phase shift. So basically you can represent this as the solution. So I should be, I mean, from the general guess, it looks like a exponential function and a sine or cosine function. Okay, so the homogeneous part is the right hand part. If you consider this as 0, so if you consider the right hand part as 0, where lambda is basically this comes from di dt. So so lambda is the eigenvalue, and if you solve the equation, you get lambda is equals to minus r by L, and the general solution of this form is C1 e to the power minus lambda t. So this is the solution of this form, because here it says that I plus derivative of I will makes it 0. So this right part will becomes 0, and this will be true if I is in the form of a exponential term. So you have a constant c e to the power minus r by l t. Am I clear?
Yes, sir.
Okay. And the particular solution is basically a sine omega t plus phi plus b cosine omega t plus phi. And a and b can be determined from the initial condition. So when you have the initial condition was the current, if the current was 0, so you assume that I is equals to 0. And from these initial conditions, you can calculate a and b. So you find out a value and b value, and replace this a and b here in equation 1.4 to get the particular solution, and you have the transient solution here, c1 e to the power minus rlt. So basically, this is the particular solution, and this one is the this transient solution here, which decays. As you can see, this is c1 e to the power minus r by lt. And after a certain time, this one goes down, right? This is exponentially decaying e to the power minus. And you have a certain part, which is basically sign of something. That means it's oscillating, so it's not decaying. So the overall current solution, the complete solution, will have a transient part here and have a steady state part here. Okay, so as it's seen here, so the current will have a basically, as the DC component decays down, you have only the steady state components. তাই তো নাকি?
Yes, sir.
So this is the case, for instance, when you have a short circuit. So let's say you are closing so let's say you have a breaker placed here. So if you have a circuit breaker placed here, let's say CB, and if you close this circuit breaker in a short circuit condition, or if you have a short circuit, then the current that flows through it will, in the previous case, it was flowing a very small current because of the load, and then suddenly you will have a short circuit current. So this short circuit current amplitude, the steady state part is high, and on top of that you have also a transient part, which in the beginning will be high, and then it will gradually damp out. This comes from, again, this, because of this C1 e to the power minus r by lt. So because of this e to the power minus r by l, as it's damps out. So you can see that this part is basically damping out, and multiplied by this is this part gives you the DC component part, and then the bottom part gives you a sinusoidal current, because you have a certain amplitude, which is basically Emax divided by the impedance. So this is square root of r square omega L. So this is the magnitude of the impedances. So is Emax divided by square root of r square omega square L square. So that will give you the current magnitude, and it will have a sinusoidal part like this. So this is the sinusoidal part, and that then you will have a superimposed DC component. So this DC component is in the beginning, when t is equals to 0, this e to the power minus 0 means this is 1. So this component is depending on the time when the short circuit is happening. This can be the magnitude 1 of the source. So in the beginning, depending on the time when the short circuit is happening, it can go as high as twice times the the steady state current. So this is what is can be seen from here. আমার কথা কি বুঝা যাচ্ছে? So if this sine part becomes 1, so in the beginning, this t is 0, So this part is 1. So if the sine part is also 1, if phi minus 10 square omega L divided by R, this part becomes 90 degree, then sine of 90 will become 1. So for a certain phi value, you will have the DC part will be the same as the maximum of the sine part, or the maximum of the AC part. So it will basically add in the beginning, it may go as high as twice the amplitude of the steady state current. Am I clear?
Yes, sir.
কারো কোনো কোয়েশ্চেন নাই এখন পর্যন্ত? সব কি বোঝা যাচ্ছে? So if you do not have any question, either you understand everything or you are not able to make it clear to you. So is it clear for everybody?
Yes, sir.
Okay. So second comes the switching of LC circuit. So similarly, in case of LC circuit, you have, if you apply this KVL here, Kirchhoff's voltage law, then you have E is equals to L di dt, and then 1 by C integration of I dt. This is the voltage drop across these capacitors. So in the previous case, it was LR circuit, and it was a first order differential equation because you have only one derivative here. But now if you have an LC circuit, it will make into a second order differential equations, because it will be d square I divided by dt. If you do the derivation again, then you will have 1 over ci, and then you will have E di dt equals to L d square I dt. So to solve the differential equation, it is transformed into Laplace domain, and after transforming into the complex Laplace variable, this can be written in this form. So this is just a simplification from this part, from the so you can see this E minus V of C, so V of C, E minus V of C, and then you rearrange this complex variable P. So you rearrange it from equation 1.11, you will get 1.12. And if you set the initial condition of I is equals to 0, then you will be able to calculate. So let us assume that there is no charge on the capacitors. Therefore, V of C is equals to 0. So that is another initial condition, and then I of 0 is equals to 0. So in the beginning, when T is equals to 0, the current was 0, and when the current was 0, the voltage across the capacitors was 0. So you assume these two cases. You need two initial conditions, as this is second order equation. So for a first order equation, you only need one initial condition, and from there you can calculate IP from here by using I of 0 is equals to 0 here, and VC0 equals to 0. You simplify this 1.12, so I of 0, this part becomes 0, VC0, this part becomes 0, and then I of P will be basically E over L, and then if you simplify here, so this will be in the denominator, it will be LC, in the numerator. If you rearrange, you get something. IP is equals to E root over C by L omega naught divided by P square plus omega naught square. Omega naught square is basically 1 over L by C, which is the frequency of this LC circuit. So from here, replacing this V of C and I of 0 with 0 values, you will be able to get I of P. And if you do the inverse Laplace transform, then you get I of T. So instead of the frequency domain, you now go to the time domain, and you get this E root over C by L sine of omega naught t. So that is the current equation, where omega naught is root over 1 by root over LC, and from the current equation, you get the VC, or the voltage equations here. Similarly, for RLC circuit, you have R, L, and C, and if you apply the KVL here, so this is the source term, L di dt plus Ri 1 over C. This makes the second order differential equation, d square I dt. And for the homogeneous part, you do not consider this source, so it will be 0. That will give you the transient response. And this homogeneous part, you can write this as a quadratic equation, and solving this quadratic equation like this. If you solve this quadratic equation, you get the roots of this quadratic equation, like R by twice L. So if you solve this quadratic equation, you get this root. And this lambda 1 and lambda 2 will, depending on the value of this R divided by 2, if the square root, if it is negative or positive or 0, depending on that, you will get the system response, if it is over damped or under damped, or so depending on this R divided by twice L, if this is higher than 1 by LC. So if this part is higher than this, that means that you will have a positive part of the square root will be, if this part is positive, then you get the transient oscillation over damped. If this part is equals, that means that this is basically 0. So if these two part is equal, so root over 0, that means the roots are of only R by twice L. In that case, this is critically damped. And if you have a negative part, that means the roots are complex, and for that you will have oscillating. Okay, so if you have a negative 1 by LC, if this is higher than R divided by twice L, then you will have a square root of negative part, which will give you a basically a imaginary root, and for an imaginary root, it will be an oscillating response. So you will have a response like this if this is oscillating, if this is imaginary, and for critically damped and over damped cases, it's like this. So if you have any question up to now, please feel free to ask. So is there any question? সবার কি বোধগম্য হয়েছে জিনিস?
Yes, sir.
I
Yes,
think
sir.
it's not. If I were you, I think it was not very straightforward and clear for me. So what I suggest to you is that go through the chapter 1 that I just covered. So this is the end of chapter 1. So go through all these 3 cases. Go through the book. You have the examples showing how this current waveform will be. Okay, and also are you familiar? I mean, how much used to are you with, for instance, Simulink or any simulation tool? How good are you in using this simulation tool? Do you use it?
For beginner
we-
level.
We used it on BSc level when at 4th year.
Okay, so
কন্ট্রোল ল্যাবে আর কি ইউজ করছিলাম আমরা, কন্ট্রোল সিস্টেমে বিভিন্ন জিনিস স্টেবিলিটি গুলো চেক করার জন্য
আচ্ছা।
সিমুলেট।
কন্ট্রোল ল্যাব ছাড়াও যে কোনো কেসে সিমুলিং বা যে কোনো it can be piece-wise as well. So you can simulate this circuit. Okay, so you can see that this is very simple circuit like RL circuit or LC circuit or RLC circuit, and you have just a source. And the problem is very simple, straightforward. What happens if you connect this RLC circuit with a source? Then you try to understand how the current waveform will be and how will be, for instance, the voltages. So I request you to go through, to build this simple models in Simulink. You can use Power Library in Simulink to simulate this circuit, or use any other software to just see the response of this RLC circuit or RL circuit or LC circuit. Okay, give a sinusoidal voltage and make a switching, and then see what's the current you get, and try to understand how these differential equations are being solved, and how these differential equations are coming, and what is meant by this root, what is meant by overdamped, underdamped case. আমার কথা বুঝা যাচ্ছে?
Yes, sir.
So please go through it, because this is very fundamental for this course. So this will be needed for you to understand the rest of the things. Clear?
Yes, sir.
Okay, so I will give you time. You can use the weekend to solve these problems, and inshallah we will have another class on Tuesday again in online, because we need to catch up with the syllabus. So if it is okay for you, then I would like to have a online class on Tuesday as well.
Okay, sir. I am okay.
Okay,
with
sir.
it.
Okay, then we will have another class on Tuesday, but the topic will be chapter 2. So we will start using chapter 2, and again for the mid syllabus, I will inshallah cover up to chapter 4. So if you want to finish it, before me, then you can start reading the book and go up to chapter 4. Clear?
Yes, sir.
Okay. আর কারো কোনো question আছে এখন পর্যন্ত? If you have any question, you can ask me.
Yes, sir. You can share the recording in the
Yes,
Google
yes, of
Classroom.
course, I have saved the recording, so I will share it with you.
Okay, sir.
Okay. Any other question?
No question, sir.
Okay. Okay, then that's it for today. I'm going to end the class then. We'll again meet on Tuesday. Allah Hafiz.
Okay, assalamu alaikum, sir.
Walaikum assalam.
Assalamu alaikum, sir.